me. This is joint work with Philipp Lücke and with Anna Niegomir, and it's actually a central part of her PhD thesis. I'm going to talk about characterizing large cardinals through forcing. And, oh, so this thing doesn't work. Now it does. Many combinatorial properties on accessible cardinals are established by collapsing a large cardinal to become one of the Aleph ends, say. And then a random example, if we collapse a Marlow cardinal, we get a failure of square kappa. And so the point of what I'm talking about is to what extent this can be reversed. So say we have this situation. So we have a theta, which is some kind of large cardinal. And then we have some collapse forcing that turns lambda plus. And then we get some combinatorial principle here. So and the question is a certain collapse forcing extension. Can we infer that if a combinatorial principle holds in the extension, we actually start with a certain large cardinal in the ground model? So that's kind of the idea for what I'm talking about. What collapse forcing to take? The first obvious candidate might be the Levy collapse. So essentially the problem is that the Levy collapse is isomorphic to the product with itself. So if you have some combinatorial property holding in a Levy collapse extension, well, you can never know that you had a large cardinal in the ground model because you might be in your intermediate Levy collapse extension where the large cardinal was already collapsed. Well, what can we do? I mean, there's various ways to avoid this, and one could try things with the Levy collapse still. But I'm not going to talk about this. The easiest way to avoid this is to not use the Levy collapse, but use some other collapse forcing instead. And we looked at Niemann's pure side condition forcing. I'm going to talk about it in a moment, but I'm not going to give any details on it. But yeah, it's some collapse forcing that Niemann came up with in a somewhat recent paper that actually has been around for quite a while. So we came up with something that we called internal large cardinals, and actually to advertise these is kind of maybe the main point of my talk. And we can use those internal large cardinals, I will of course tell you what they are, to characterize inaccessible and Marlow cardinals, pi mn indescribables for any m and n, and subtle and lambda ineffable cardinals in this sense that I sketched before. And we can also use the classical notion of generic large cardinals to characterize in the same way larger large cardinals, namely measurables, gamma supercompacts, almost huge and super almost huge cardinals. Let me very briefly talk about Niemann's pure side condition forcing. I mean, I think I'm going to give the definition and not say much more about it. The click thingy, oh, it does work. So we start with some infinite cardinal theta, and then we define this collapse forcing p theta. To define this forcing, we first define a set S theta of countable elementary submodels of H theta, and a set T theta of transitive and countably closed elementary submodels of H theta. And so what are conditions in this forcing? They are finite epsilon increasing sequences of models, and these sequences are closed under intersection. So if you have two models in this sequence, the intersection is in the sequence as well. And the ordering is reverse inclusion on the range of its conditions. So if the sets appearing in one condition are more than the sets appearing in another condition, then this condition is strong. To know much about Niemann's pure side condition forcing, really. All you need to know is that it's some other form of collapse forcing, and I'm going to try to advertise our results that you can characterize large cardinals with it. And a few details about this forcing will come in during the rest of the talk, but as I said, you don't need to. So if you don't know this forcing, don't worry, you should still be able to perfectly follow the talk. So the very basic case is that of what we called countably inaccessible cardinals. So I think there's no established name for this. It's no large cardinal, it's just a regular cardinal which is closed under omega, under powers by omega. So if you have some delta less than it and you take its power by omega, you're still below your cardinal. So if anybody knows an established word for this or is unhappy with countable inaccessibility, let me know. So that's what we called it. And so one property of Niemann forcing is that if you start with a countable inaccessible cardinal, Niemann forcing, so p theta is now always going to be Niemann forcing at theta. It preserves omega 1 and theta, and it collapses all cardinals in between, and it satisfies the sigma approximation property. So this notion due to Hampkins. If you don't know what that is, I'm not going to use it in any technical way as well. And so all these results are essentially due to Niemann. I think he proved it for inaccessibles rather than countable inaccessibles. But it's the same proof, really. So we get the first lemma, which is almost the characterization of what's not quite a large cardinal. So it's equivalent to start with a countably inaccessible cardinal and, to have Niemann forcing turn it into omega 2. So that's pretty much following our scheme, or the scheme that I sketched on this blackboard. So we start with some, well, let's say large cardinal for now, even though it isn't, and we get the combinatorial property in the extension, and it's an if and only if relation. Yes. Okay, next one is inaccessible cardinals. And in order to characterize inaccessible cardinals, we need a notion of a weak corepertory. It's a tree of height omega 1 and of cardinality aleph 1, and it has at least aleph 2 many branches. As you may immediately notice, if CH holds, this is pretty boring because the full binary tree of height omega 1 is a weak corepertory, but it's an interesting notion if CH doesn't hold. And if we perform a Niemann collapse, CH won't hold. And, well, fairly standard arguments show the following, and that's our first real large cardinal characterization. So it's equivalent to start with an inaccessible cardinal in the ground model and to get that there are no weak corepertories in the Niemann forcing extension. Right, so note that theta is collapsed to omega 2 in this extension because, of course, an inaccessible cardinal is countably inaccessible. Okay, so this doesn't quite have the shape of a characterization, but of course, if we add in the second clause that theta has to be equal to omega 2, then this is exactly, then we can remove this assumption of countable inaccessibility in the lemma, and we get the characterization of that form over there. Okay, so before I talk about further small large cardinals, let me jump to the large cardinals for a second. Making strong use of ideas that appear in proofs of results by Matteo Viale and Christoph Weiss, we get the following characterization. So if you start with an inaccessible, it's equivalent for this inaccessible to actually be gamma supercompact in the ground model, or to have a Niemann forcing force that there's a partial order with the sigma approximation property, which witnesses that omega 2 is generically that level of supercompact. Similarly, we can use Niemann's forcing to characterize almost huge and super almost huge cardinals to their respective generic counterparts. So this is just a quick jump to the large cardinals, for which you have characterizations with embeddings which just map the large cardinal as the critical point. So I'm not going to talk any further about this. I'm going to jump back to large cardinals which are compatible with V equals L. And for these large cardinals, we kind of developed an analog of generic large cardinals. And these are our internal large cardinals. And they are based on small embedding characterizations. So what is a small embedding? A small embedding, so maybe I'll draw a picture. A small embedding is an embedding which goes from some model M. So it's here. That's our small model M, so maybe that's why we call it small embedding. So it goes from our small model M into the much larger, so M is transitive, it goes into the much larger H nu. And it maps, in particular, it maps the critical point. So that's our embedding J here. It maps the critical point to, what is it, theta. Oh, so this arrow should go in here. So that's a small embedding for theta, and the idea is that theta is a certain large cardinal. So that's the idea of the small embedding. Well, and there's a very classical result on this, which is due to Magidor, and it's very old. It states that theta is supercompact if and only for every nu greater than theta, we have an alpha less than theta, and an elementary embedding, which goes from h alpha to h nu and sends its critical point to the supercompact cardinal. So that's exactly this picture over there, except that M is now additionally required to be some h alpha for alpha small. And yeah, in fact, there are small embedding characterizations for many other large cardinal notions. So that's what I'm going to talk about for a bit. Well, actually not, I think. I'm only going to give one example now. So for a very small large cardinal, namely a Marlow cardinal, this is kind of a folklore result. At least it appears in papers of Magidor and maybe even earlier. So it's equivalent to have a Marlow cardinal or to have a small embedding into an arbitrary h nu, which maps the critical point to your cardinal and satisfies that the critical point is regular, plus the model M contains all of the universe up to the critical point J. So that's, I mean, it's easy, it's an easy lemma. So this is equivalent to a Marlow cardinal. And oh, the thingy doesn't work again, I think. Oh, it does. Okay, so yeah, so these small embeddings, you all work the same way, kind of. So we have this embedding from some small model M into h nu. The critical point is mapped to the supposed large cardinal, and then we have some additional properties. So in this case, critical point is regular, and the model contains this initial segment of the universe. And so we call this a correctness property because it's a property which states that to some extent M and V agree on certain things. So for example, in M, the critical point is of course regular by elementarity of the embedding, and so we asked that it's also regular in V. So this is kind of a correctness between M and V. Well, and the second property that we have here obviously is as well. And the second remark, which, well, kind of comes up in a second, we can also require any given x in h nu to actually be in the range of J and still get an equivalent condition. So that's just a technical detail. And the point is somehow that we can turn these small embedding characterizations into combinatorial properties that we call internal large cardinals in quite a canonical way. And this way is canonical in the sense that it works for many types of large cardinals in basically always the same way. There's some text here, and I think I'm going to try and draw a picture. So the idea is somehow that now we have an embedding which characterizes our large cardinal, and so think we have a collapse forcing. So let's say we have a collapse forcing P. And if this collapse forcing is sufficiently nice, so it's supposed to turn theta into some successor cardinal. If this, then it's going to be a subset of h theta. And, well, we want it to have some nice properties. And the point is it should be nice enough so that we can lift this embedding to the generic extension. And then the picture somehow is that this M, maybe let me move the letter M inside. This M is now contained in some larger model N. This is our model N. And so let's say the forcing also has this property that somehow P crit J, well, is a complete subforcing of P theta or so. And then we get, let G should be P generic, and G bar should be P crit J generic, so generic for the forcing up to crit J. And somehow the picture we get is, okay, well, we have some my picture is pretty bad now. We have some forcing extension of this small model. This is supposed to be m of g bar, so just extend it up to the critical point. Whoops. And here we get h nu of g. And the embedding now goes, let's call the lift. J goes from m of g bar to h nu of g. So if the forcing is nice enough, that's kind of the ideal situation we want to have. And the idea of internal large cardinal properties is now to isolate as much of this as possible into a combinatorial property of the forcing extension. So that should be what I wrote up there. So if we go from a small embedding characterization to an internal large cardinal, we require the existence of an inner model n of h nu. So we are now in the generic extension by our forcing. So that's n of h nu of g in this picture. We require that the small model m is in there. Oh, sorry, I forgot to say one thing. The idea is, of course, that n is h nu of g bar. So that's the inner model if we just force up to the critical point. So we require the existence of this inner model n. We require that m, which is kind of m of g bar in this picture, is an element of n. And we relativize the correctness property that we had for the small embedding characterization between m and v. We just ask this to hold between m and n now. And then, depending on the forcing we use, we also require some kind of relationship between n and h nu. So for example, with Niemann's pure side condition forcing, the tails have the sigma approximation property, and that will be exactly what we require between n and h nu, because that's what we will get if we are in this situation. Okay, so that was the notice to me, but I already did it. I drew a picture, just in case I wanted to forget. Okay, so that's the definition. It looks a bit long at first, but it's kind of natural, and it looks almost the same for all other types of large cardinals that we will consider. And most of it is in the picture. So we say theta is internally Malo if for all sufficiently large regular cardinals nu and all x in h nu. So that's all not important. We have this small embedding now, which goes from m to h nu and maps its critical point to theta, so the internal large cardinal. X is supposed to be in the range j, and we have a transitive model n of z of c minus, so that's this inner model over there. Yeah, so it's supposed to be a subset of h nu. We have the sigma approximation property between n and h nu. M is in n, and then that's kind of, so if you remember the Malo cardinal, for the Malo cardinal we had h crit j subset of m, and we had crit j regular. So that was the small embedding characterization of Malo cardinals. And now we have essentially the same thing here in 2 and 3. So in 3 we say crit j is regular in n instead of v. And well, we weakened h crit j subset of m slightly to p omega 1 crit j of n is a subset of m. I guess it should also still be equivalent if we ask for h crit j to be a subset of m in 2, but for other large cardinals it's more natural to have this here, but yeah. So think of just the items that we had for the small embedding, I've moved over there. This easy lemma, if theta is internally Malo, it's regular and uncountable, and there are no special theta Aronshine trees. And then we get the following characterization. So if we start with an inaccessible cardinal, that inaccessible is Malo, exactly if Niemann's pure side condition forcing forces omega 2 to be internally Malo. And again, if and only if p theta forces, there are no special omega 2 Aronshine trees. So that's two forcing characterizations of Maloness by properties 2 and 3. So, oh, I have a proof, but I think it's not much of a proof. So from 1 to 2, that I did in the picture, 2 to 3 is the easy lemma, which I didn't prove, but yeah, it's a proof here. And 3 to 1, well, it's essentially looking at some stuff by Todorcevich, and he has a notion of special arrangement trees at inaccessible cardinals. And yeah, it's modulo this, it's an easy argument. Okay, so I only have a few more minutes. Let me try and go faster. Maybe not. Let's see. So the next one is internally indescribable cardinals. So we have a small embedding characterization of indescribable cardinals, which I'm not going to tell you due to time limitations. We also get an internal version of indescribable cardinals. And so far, I only copied stuff that is exactly the same as for internally malus. So this is all the same. And then we have one extra requirement, which suddenly appeared now. And that's some correctness property for pi-mn formulas between h grid j of the model and h grid j of the intermediate model n. And that's, again, so if you see this, you can kind of go back and infer the small embedding version of indescribables, because it's just copying these properties over. Okay. So again, the situation is very similar to before for pi11 indescribables. So if you have an internally pi11 indescribable, it's regular and uncountable, and it has the tree property holding. And then we get a characterization result, which also looks as before. If you start with an inaccessible, it's pi11 indescribable exactly if Niemann forcing turns it into, if Niemann forcing forces that omega 2 is internally pi11 indescribable, exactly if Niemann forcing forces omega 2 to have the tree property. So I guess so far you could complain that we could just omit these internal things because there are nice combinatorial properties which characterize these large cardinals through forcing anyway. So there's maybe not much point in what I've done so far. But the thing is, we can do this now for higher levels of indescribabilities. Oh, one remark, 1 equivalent to 3 is where he introduced the forcing. So the point of this really is that now we have, well, maybe something which could be considered as a slightly stronger analog of the tree property as the combinatorial essence of higher levels of indescribability. Because there seems to be, or at least I don't know of, any combinatorial principle which is kind of parallels in higher levels of indescribability as the tree property does for pi11 indescribability. Yeah, so as for the pi11 case, we also get in the pi-mn case that theta is pi-mn indescribable exactly if Niemann forcing forces omega 2 to be internally pi-mn indescribable. And yeah, there's a moreover. If you have an internally pi-mn indescribable that is additionally inaccessible, then it's actually already pi-mn indescribable. So the idea is somehow that internal pi-mn indescribability is kind of, if you just destroy the inaccessibility of such a cardinal, that's what's left somehow. That's at least a very strong fragment of what is left. One last slide about something different, or not quite, but yeah, similar things can be done for subtle, lambda ineffable, and supercompact cardinals, which is very closely related to notions introduced and studied by Matteo Viale and Christoph Weiss again. And I think, oh, yeah, well, that's it. Thanks.